Hello everybody, this is your introduction to the Total Synthesis Project. I would recommend you going to the Total Synthesis Project pages in your lab manual. I think it starts around page 81 or 82. The objectives of this project is to make up lost lab time. So since we're not going to be in the lab, we're not doing a lab practical, and to make up for one of the experiments that we're not doing. This will also be a good way for you to review reactions before the final exam. This is good practice for multi-step synthesis. This will be much larger molecules than you're used to seeing. And you'll also get some practice in preparing a poster. What exactly is a total synthesis? It is a stepwise synthesis of a large molecule. They often, or almost always, include a retrosynthetic analysis. So you get one molecule and you can kind of work backwards to see where it makes sense to break things apart. This type of synthesis is done all the time with natural products. So you can see all of these natural products here that have been synthesized. Several of them are very scary looking projects, but yours will not be as bad. And notice that some of these have stereocenters that are very specific. You will not have to worry about stereospecific molecules. Your guidelines are that all starting materials must be commercially available. So you can't just make up reagents out of thin air that may be very convenient for a synthesis. You have to be able to purchase them somewhere. A good place to look for that is Sigma Aldrich, or you can use SciFinder. That will help you find out if something is commercially available or not. Your materials can only have 6 carbons or less, so you could not use benzoic acid. If you wanted to use benzoic acid in your synthesis, you would have to do a reaction in which you can create benzoic acid. You can use phenol, but you cannot use benzoic acid. So you can have 6 carbons plus a functional group, just not more than 6 carbons. You can use any reaction from organic 1, organic 2, or from the literature. If you do use something from the literature, it must be referenced. And you also should be creative in your synthesis. In the process of it, you want to do a retrosynthesis. Look for disconnections where you can find functional groups. That's usually a good place to disconnect things. And keep track of your numbers of carbons that are added or are needed. This is a synthesis that I did in graduate school for Calelactone A, which is a natural product. The molecule itself doesn't actually look that complicated, but the proposed synthesis that I had was in total 55 steps. I had to create 6 stereocenters using different reactions including Evans aldols, Sharpless dehydroxylations, Mitsunobu inversions, and a Ramachandran and Brown's reagent called dip chloride. So I don't remember what the last 2 reagents are at this moment in time, but I'm sure in graduate school I knew what they were. But you can kind of see the general retrosynthesis. You can see different disconnections in the molecule. So the last step here was to close the ring. One of the things that you want to think about also is that you don't have to do a linear synthesis, and we'll see that on the next slide. But with this retrosynthesis, even though it took me 55 steps, my retro is just about 10 steps of retrosynthesis. So you don't have to break down every single step backwards, just kind of general pieces. And my starting material was a nitrile here. So this is just a fake target molecule. And for me to do the synthesis here, the retrosynthesis, I broke it down into a couple of different parts. The first one here is I would imagine using an alcohol plus an acid chloride in order to close up the ring. And this part of the molecule here comes from 2 different pieces. So I can have this part of the molecule that has a Grignard and a protected alcohol, plus this other part with a nitro group here. So, and then you can look at different ways of going stepwise back to something that you're familiar with or that only has the 6 carbons. So you might get to a spot where, well, maybe I can find a better reaction for this that's faster. So that's why I have that circled there. Here I have this reaction with an epoxide. And then I further break it down into propanol and this phenyl magnesium bromide. So again, there's a benzene here. There's a functional group that both of these things are things that I can purchase. You can also use SciFinder to research new or more efficient reactions. You can find it where this structure, this fragment that I'm looking for is a product. You can also look for reactants or reagents, any of those things there. So if you were doing forward synthesis with just your organic reactions, we'd have Br2 FeBr3, and you could use NaOH plus at 350 degrees, but that's a very harsh condition, so you may lose the acetal in that. So you want to look for a different way that you can make that. So if I do this search here to get an alcohol, there's different steps here that would work for that. And you can just reference that reaction with the copper catalyzed hydroxylation in the literature. That doesn't require 350 degrees. So the forward synthesis, this is where you do have to go stepwise. One thing that you do not need to do is indicate what is changing in a different color. I know that's going to be tricky for you guys. But for this synthesis, this is a presentation from when I gave it this summer where the students had to do an actual oral presentation. You just need to put all these steps onto a poster in a way that makes sense. So I have here in the upper corner just the parts of the molecule that I'm working on this particular slide. So we can start with catechol. We add bromine via a reaction that we already know. This is an ortho-para director, so it can direct para to one of those alcohols. Dichloromethane will get us the acetal here. And that is a reaction that you could look up. That one probably should have been referenced as well. And this is the step that we saw from SciFinder to add the OH on that group there. In the next step here, after we've added the second Br, I'm going to protect my oxygen, my alcohol, with the TBS chloride, and that's a tert butyl dimethylsilyl-chloride, and then I make that a Grignard. The Grignard plus this propanal, both are commercially available. I can do this reaction here to get the alcohol, and then I'm going to add sulfuric acid, that is para, to this group here, and then add a nitric acid, oxidize my alcohol, use LDA. That's going to do enolate chemistry, and I'm going to do a Michael addition to add that there, and that chemistry we'll see on Wednesday. After I had this aldehyde here, I'm going to oxidize it to the carboxylic acid, convert it to the acid chloride, then go to the next part of the molecule. In hindsight, now that I'm looking at this, it might have been a better idea to use the copper lithium here. I'm going to protect both of these ketones with the ethane dithiol, so I would use this in excess. And then with that piece, I will reduce my nitro group with zinc and HCl, add sodium hydride, and react this nitrogen with the epoxide. Alright, so once we've added the epoxide, that'll give us the alcohol. That will get oxidized using the Jones reaction. I convert that to the thionyl chloride, and then I'm going to use TBAF to remove the TBS chloride. And there is my molecule. Alright, so when you're presenting your synthesis on a poster, we don't need the typical sections in a poster. We don't have to worry about the intro methodology because there's no history to your molecule and it's a made-up molecule. You're not going to see those things. So really the two things that you need on your poster are the retrosynthesis, which needs to be general. I do not require a step-by-step retro. You'll go back to the slide with my retrosynthesis. It was very general and there was only 10 or 12 steps where my synthesis was much longer. You need the actual forward synthesis. The size of the poster that you use does not matter because we're not printing them. So if you want to do it small, you can, or you can do it on a regular 36 by 48 inch poster. That's fine. It should have a logical flow, so I shouldn't need directions on how the poster is going to flow. So you shouldn't start in different chunks. If you wanted to do different components, you can do different boxes where there's parts of molecules and then bring it together in the bottom. That's fine. The fonts should be legible in both style and size. It should be visually appealing. So make sure you're not using obnoxious colors. Make things align. It looks like you've put some time into it and you didn't just slap it all together. For the chemical structures, usually we'd have computers on campus that you could use to draw the structures, but that's not possible right now. So I would recommend using ACD labs. That's what my summer students used and they said that worked fine. You could use SciFinder and just do snip clips or any other drawing software that you come across. So after you finish your poster, it'll be uploaded to Moodle and you're going to be assigned to peer review another student's poster. So the things that you'll be looking for is it visually appealing? Does it have a logical flow to it? Does it include a retrosynthesis? Do you think that the forward synthesis will actually work? If you find faults in it, you want to include those as well. Did the student use chemistry not found in class, i.e. using SciFinder, and were they creative? So the next slide, 2 slides are just kind of examples. You can't see them in detail, but that's not a huge deal. But you can get an idea of the layout for a total synthesis poster and how they're kind of put together with the different reactions. So those are tall posters, and we have 2. I know that one picture on the left is terrible, but there's 2 of the landscape posters, and you can see how those are laid out there. So if you have questions on the total synthesis project, I will be posting a discussion board so that you can ask away and I can answer those all in one place so that I'm not answering multiple of the same questions. Thanks, guys.